having this basic idea is not sufficient to make it work, but it was necessary in this case. So let's step back for a second. So the deep learning, we've got these neural networks here. And what is a neural network? Well, here's a depiction of a neural network. It takes in some kind of input. In this case, it's a facial recognition network, so it's going to take in pictures of faces. And so the input's here on the left. And then after layers and layers of linear and nonlinear processing, depicted here at these intermediate blocks of images or feature maps, at the very end of the network, a decision is made. So in this case, the decision will be, which actor or which celebrity do I detect in this image? A deep neural network has to have these nonlinearities in it. Otherwise, it just becomes a linear transformation. And a linear transformation, just like a linear regression, does not have enough expressive power. It can't really disentangle all those complicated nuisances that I talked about earlier. So the nonlinearities are essential. And every time you introduce more and more nonlinearity, it essentially lets you express more and more curves in the function, more and more wiggles, if you will. So you can express much more complicated functions the more nonlinearities you have. So the basic artificial neural network architecture, of course, was directly inspired by the brain, but then we can deviate as we see fit. So what are some of the successes of modern day deep learning before we get to some of the failures and limitations, which is the main focus of this session? So the shot heard around the world back in 2012, ConvNets were the first neural network architecture to really dominate the so-called ImageNet challenge. So this is a depiction of this 12-layer neural network, and this was one of the largest neural networks ever trained at the time that it was invented. There were 7 hidden layers, 650,000 units or artificial neurons, and had 60 million parameters. It was trained on more data than any other neural network in history at the time. It had been trained on millions and millions of images of data. And actually that data was expanded out to billions of images using a trick called data augmentation. So we're now in the big data phase of machine learning where the data sets are enormous. And critical also was the advent of much, much faster computational methods, including the hardware use of GPUs, graphical processing units. These gave speed-ups anywhere from 5x to 50x over CPU, and it was critical for these developments. But of course, we cannot forget that this data set, this ImageNet data set of millions of hand-labeled images, how was that even possible? Well, it was Amazon Mechanical Turk that allowed us to crowdsource all of these millions of images and get labels for all of them. So this was a critical part of this revolution. It would not have been possible had this not been done. So after this initial success with object recognition, which is depicted here, you can see several things about object recognition. One is that the sheer amount of variation that you deal with. So for example, look at all these pumpkins, right? So there are many, many different faces of the pumpkin, many, many different pictures of the aircraft carrier with different brightnesses, different viewpoints, lots of nuisance variation. Same thing with the elephant here, right? And previously, people tried to hand design features, hand design architectures that can deal with these nuisances. Now this is all being learned directly from the data. And this on the left-hand side here, you see the kind of output that a convolutional net can give. It gives out a probability distribution over different categories. So for this task, a categorization task. So you get out these probabilities for any given input. And sometimes the probabilities make sense, in which case we call them calibrated. And other times the probabilities really don't make sense at all, and we call them uncalibrated. The interesting thing about neural networks is whether the probabilities are calibrated or uncalibrated, they seem to learn to make the right decisions. But that's already a first indication that these cannot be treated as black boxes. The probabilities that are coming out are not necessarily calibrated to reality. After this initial success, there was a huge sort of if you will, Cambrian explosion of different kinds of neural network architectures. The evolution of these different species of neural networks just became really easy to do. You could design your own neural network, train it on some data set, and within days test it out. And this ability to rapidly iterate, to define and iterate and train neural networks led to this plethora of many different species, of which we can't cover them all today, but we can look at a few. So one particular architecture was developed for facial recognition. It's called the deep face architecture. This was developed by Facebook. And it's a particularly nice architecture for facial recognition because you can see all the elements of modern day deep learning in this picture. So for example, there's still some pre-processing here, right? So I don't just pass in a raw image. I first take this raw image, I do a little pre-processing to crop out the part of the image that's going to be related to the face. That's still needed. You still need to pre-process, you still need to focus. You also need to do what's called frontalization. You need to rotate the face. Again, this is a computer vision procedure unrelated to neural networks to kind of straighten out and make the face look forward. And then after that point, you pass it into a neural network that has many, many layers of units. And you notice that each layer can be visualized as if it were an image. Right? So there's an X and Y component, and there's a bunch of channels to this image. So these are called feature maps. You can think of them as a generalization of images. As you go deeper and deeper, you can kind of still see the remnants of the original image in this second layer. But as you go deeper and deeper, these activations, these responses of these artificial neurons become more and more abstract. And we can no longer interpret what's really going on in these deeper layers. This is an active area of research to figure out, is there some mathematical interpretation of these? So using these kinds of deep neural networks, many kinds of amazing applications are possible. One can combine the content of one image with the style of another. So you can take your favorite style from a painting that you like Van Gogh's Starry Night, and combine it with the content of some other image. We won't have time to go into the details, but the fact that this is possible and that yields human, high perceptual quality images was one of the amazing things that we discovered. On the other hand, there are limitations. And when we look at some of these limitations, we can see on the left-hand side that when we train neural networks to generate digits, that they do a pretty good job of generating digits. They even learn they even learn implicitly that slant is a sort of variable that matters for generating the different digits. Right? So they automatically learn these kinds of things just by learning to generate digits. However, when you ask them to generate dogs, much more complicated set, I don't know about you, but that is the scariest looking dog I've ever seen. And this begins to show you the limitations of these neural networks. They are capturing something essential, something that is dog-like. And indeed, if you look at a local patch of pixels, it has a texture that is associated with dogness. But globally, it doesn't quite make sense. Right? So already we see that maybe these convolutional nets that were used to generate these were just modeling local correlations and somehow missing long-range correlations. So we start to see some of the failure modes. Nevertheless, people continue to progress and they design better and better neural networks. And after many years of iteration, they started generating faces with these neural networks, celebrity faces. Now, these two celebrities don't actually exist. These are completely made-up people. And I highly encourage you to, I couldn't get YouTube to work in China, but I highly encourage you to, after the fact, go watch this video and see these amazing-looking faces. Moving away from the visual domain, you not only can generate images, you can also generate text that looks realistic. So this is generating wiki markup, generating C++ code, and if you're a bit of a masochist, generating algebraic topology. So all of these three languages of which I only understand a couple. All of these languages have their own grammar, have their own syntax, and you can see that the neural networks learn a lot of the syntax, a lot of the grammar. However, if you notice, the text is semantically meaningless. This code does not even compile. It looks like C++ code, but it's completely meaningless, right? Same thing with the algebraic topology, but I wouldn't be able to tell. So again, we see the limits of deep learning. We see that you can learn a lot of syntactic structure, but semantically, it's meaningless. Of course, there are many other applications of deep learning which we don't have time to go into, one of which is a neuroscience application. It turns out, and this is one of the, I'll skip the slides due to time. It turns out that much to the chagrin of many neuroscientists, our best models of responses in the visual cortex are currently deep convolutional neural networks, achieving an R-squared of roughly 50%. This means showing natural image or synthetically rendered image inputs to a monkey and also to a neural network, both able to do the same task of object recognition, and then seeing how well you can predict the responses in the brain off of the responses in the neural network. And that's where the R-squared of roughly 50% comes in. And roughly, it seems like later layers roughly correspond to later areas in the visual hierarchy. So this seems to suggest that even though deep convolutional nets are not neurally, or maybe they're not neurally plausible, there is something similar about the representations that they end up learning from the ventral stream in the brain. This was a bit of a surprising finding. Nevertheless, now for some cold water. So deep learning still has many things that it struggles with. And one of these things that it struggles with will be very important for its applications in the natural sciences. So in particular, you've probably heard about the Tesla autopilot accident. That was, I couldn't actually even find an image of it on the internet anymore. They've taken them all down. But a Tesla, a neural network in the autopilot miscategorized, one more minute, miscategorized a tractor trailer as a billboard. So, and because it was a billboard, it vetoed the radar and said, ignore the radar's warnings. And so unfortunately, the Tesla driver ran right into the tractor trailer and died. So that was, I think, the most prominent error that a neural network has made. But it just goes to show you that you can't just trust the black box. It's not interpretable, and before you put it into something as dangerous as a car, we really need ways of formally interpreting and verifying what's going on under the hood. Another disturbing aspect of deep neural networks that seems extremely robust is that they are prone to so-called adversarial examples. So you see here on the right, I can take a picture of a panda, and I can add some adversarially chosen noise to it that is, and it gets this new image, which is humanly imperceptible. There are imperceptible differences between the input and the perturbed image, and yet the convolutional net is 99% confident that this is now another animal. And you can make it think it's a school bus if you want to. It's really bad. So obviously our brains don't do this. Our brains, so far as we can tell, our brains are not prone to such adversarial examples. But it suggests that there's some really weird input-output instability in these neural networks that we have not been able to alleviate. And finally, the most critical thing for natural science applications is that deep learning has poor generalization when extrapolating outside of the training set. And so let's go a bit into what we mean by that. So what are some applications of deep learning in the natural sciences? The key one is automation, right? So this is where you try to automate away tedious and time-consuming or costly perceptual tasks. But the more flexible modeling application is the one that we really care about, is how do we model large, complex, nonlinear systems. So I'll jump ahead and show you an example of what happens when you pit deep learning against recurrent neural networks, and this will motivate the next two talks. So here on the left, I've trained a system that really understands the dynamics of basically it's a bunch of coupled oscillators, a bunch of pendulums